Okay, good morning. Today we're going to be doing a lecture on how high-gain observers work. We're going to be focusing on the book called Nonlinear Systems by Khalil, but we're also going to mention a few things from this paper, which is high-gain observers in the presence of measurement noise. Switched gain approach. And that's going to be by Ahrens and Khalil. And so we're going to also use that as motivation for some of what we'll talk about. But primarily we'll be looking at Nonlinear Systems by Khalil. So this though paper, I'm going to call this the High-Gain Observer paper. And I'm going to call the other book Khalil. So the High-Gain Observer paper is for output feedback control using high-gain observers with measurement noise for a class of nonlinear systems. And so the specific class of nonlinear systems that's considered in that work is the following. It's x dot equals ax plus b phi of x z d u, z dot equals phi of x z d u, y is cx plus mu for noise, and then w is theta of x, z, and d. And so, with regard to this, the requirements that are used in that high-gain observer paper are that u is single input, so it's contained in R. Then also we have x is a state, it's contained in R to the R, and we call that the external state, and then they call this other one z the internal state, so these are both states. And then the differentiator between these states is that one is going to be used in the state feedback controller, and one is not. Then we have y contained in R, so this is a single output that has the noise here. And then W is also an output, but that should say S. But this one isn't in this form, this one's in a different form, so you can see this one doesn't have the noise and it also isn't the linear type, and they're going to be used differently. So mu is also here is the measurement noise, and so because y is one-dimensional, so is nu. So the requirements for this class of systems are also a little bit stronger than this. They require that the A matrix has this form, so like 0, 1, dot, 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 0, and then 0, 0, 1, dot, 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 etc., down to 1, and then a 0. So then there's zeros above and below this, but it's not on the diagonal, it's like one above the diagonal is the ones. So then the B is equal to 0, 0, dot, 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 and the last position there's a 1, and then the C is 1, 0, dot, 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 0. And so we can then say, well, what does this kind of look like if we were to write out an example of what that would be? So here's the way that sort of looks. So it comes out to be something like this. x1 dot is x2, x2 dot is x3, dot, 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 xr dot is phi of x, z, d, u, z dot is psi of x, z, d, u, y is x1 plus mu, and w is phi of x, z, and d. So you'll see that this is actually a very, very specific form. So in the Khalil paper and in the High-Gain Observer paper and in the Khalil book, it says that this type of, like, examples of where you could get systems that meet this description is through input-output linearizable systems, and then also with some types of mechanical and electromechanical systems where you have measurements of the position, but you don't have measurements of its derivatives like velocity and acceleration. And then, so in chemical engineering, it would be relatively atypical for you to start with any kind of process model that looks like this off the bat. And so what that means is that in order to be able to use this, probably you need an input-output linearizable chemical process system for this to make too much sense. And then so the question then becomes, how would I develop an input, like what is an input-output linearizable system? How do I get that? So let's talk a little bit about feedback linearization. So now we're going through a chapter in Khalil. Specifically, we are going to chapter 13, which is the chapter on feedback linearization, and we'll do a little bit of this. So with feedback linearization, linear systems are known to have a lot of dice theory. They're motivated, so we're motivated to try to see when can we make a nonlinear system look like a linear system. And so there's been a lot of work where people have tried that in many different ways. Of course, we don't have to do that, but historically, people have liked doing that because it makes systems pretty easy to analyze theoretically, and then just, as you know, a lot of, not as you know, I don't know who the audience is, but for nonlinear systems, a lot of times the mechanisms that we have for assessing stability are much more challenging than just like a linear system where you basically look at eigenvalues most of the time. And that can be done on a matrix relatively easily. Even MATLAB can run the algorithm. But then for nonlinear systems, a lot of times you have to get a Lyapunov function, you have to look if it's always negative, and all these different things. So if you can make a linear or a nonlinear system into enclosed loop into a linear system, then you can very quickly assess stability of your steady state, for example. And so from one perspective, like you could say, well, that's a little limiting because it means that I have to be able to linearize my system. That's true. It's also very strong in the way that it allows you to very quickly make assessments about stability without going through a ton of extra work finding functions and seeing if they're negative along the trajectories of your system and stuff like that. So because of that idea of what's the linear system good for, people have wanted to try to see if they can design controllers that make a closed-loop system in some coordinates be linear, so that then they can make stability judgments about the nonlinear system's origin with linear control theory as opposed to needing the nonlinear control theory tools for the reasons that we just described. So that means that this problem of feedback linearization has been a problem that is of interest in the literature. And so say we start like this. So x dot equals f of x plus g of x u. And y equals h of x. So say we have this system, then we want to know if we can devise a clever u over here, and maybe we need a change of variables of the problem as well, to be able to make the resulting closed loop dynamics linear so that we can analyze them. So right now we're going to say, can I make the resulting system over here have enclosed loop when I choose a certain u, have 0 at the have the origin be 0 and have the essentially the new system be linear so that I can analyze whether or not the origin is tracked based on eigenvalues. So here's an example. So here we have x1 dot equals x2, and then we have x2 dot equals negative a sine of, sine of x1 plus delta minus sine of delta minus bx2 plus cu. So this system, if I was to choose u as basically whatever could cancel all this out and leave me some linear stuff, I could say u is equal to a over c times sine of x1 plus delta minus sine of delta plus v over c. And then, so you might say, what's this v? Well, what this v is it's the part that's going to get left. So when you plug in this u, you're going to get back x1 dot equals x2, and you're going to get back x2 dot equals negative vx2 plus v. So what is v? V is the part that's left after you use this control law. And then so its role is going to be that you want to choose it so that you're left with a linear system over here with the eigenvalues being negative. So you want to choose V as some linear combination of x1 and x2 that achieves that goal. And so for example, what could you choose? So for example, if you choose V as negative kx1 minus k2, or k1x1 minus k2x2, that is a linear combination of x1 and x2. What this would give you is it would give you x1 dot is x2, and it would give you that x2 dot is negative k1 x1 minus k2 plus b x2. And then so you choose now k1 and k2, which are in your v, so that you make the eigenvalues of this resulting system to have negative real part. And so that's really nice if I want to essentially let me quote unquote quickly design an asymptotically stable controller. And so that's really cool if I can do that, but can I always do that? So the answer is no. You really need a special class of systems. So you need a class of systems where any nonlinearities that exist can be canceled by the u. So that means that any that are added, you have to be able to like subtract off part of input and multiply by whatever term, the inverse of whatever term is in front of your u, in order to be able to cancel them. So specifically, in order to be able to do this feedback linearization idea, which is what we just did, you need to be able to have a system with this kind of form. So ax plus b gamma of x times u minus alpha of x. Because then, if this is true, then if you choose u is alpha of x plus gamma inverse of x v, now you're able to be left with a system where you can choose your v in order to make the eigenvalues of the resulting linear system be negative. But so if you don't have that, then you can't really do this. So in general, we don't have a lot of systems, especially in chemical engineering. Sorry, this is X. We don't have a lot of systems in chemical engineering that just look like this off the bat. And so what we need to do is we need to know, like, is there any system I can make look like this in new coordinates? Because if I can stabilize the system in the new coordinates, then that tells me something about what goes on in the old coordinates. So I can try change of variables to see if the system is linear in another set of coordinates. So let's look at that. So here's another example. So we can say here's x1 dot equals a sine of x2, and here's x2 dot equals negative x1 squared plus u. So in this case, even if I choose u is x1 squared plus some type of nu, for example, it doesn't matter what nu I put here or how many linear terms I have down here. So even if I cancel my nonlinearity and this part is very linear, there's nothing I'm able to do with my u to influence this part. So there's nothing I can do with my feedback in order to make this part of the system be linear. So then you say, oh, what can I do? I guess I can't analyze this with feedback linearization. Well, that's not actually true. You could still design a U to make the origin of a changed set of coordinates be stabilized, and that your controller that you have in those changed coordinates could be one that causes the system dynamics to be linear in those new coordinates. So pretend I'm lucky enough that I think of this, that I say, oh, hey, I got this clever transformation idea. Let me define a new state z. I'm going to call z1 equal x1 and z2 a sine of x2, which is x1 dot. Sorry, it says x1 dot. So now, then we can write z1 dot is equal to z2, and we can write z2 dot is equal to a cosine x2 times negative x1 squared plus u. This just comes from This just comes from doing the chain rule here. So you can figure out what these are in terms of Z1 and Z2. So you could, for example, everywhere that it says X1, it will be Z1. You could figure out what's the X2. And then, and the way you do that is you can find, here it's really easy to find the inverse transformation. So you just say like, oh, X1 is Z1, and X2 is sine inverse of Z2 over A. And so this is well defined if negative A is less than Z2 is less than A. So this is locally invertible. And then, so now I have my new coordinates. And so what I can do is I can say, okay, I'm going to set U is negative x1 squared plus, U is x1 squared plus 1 over A cosine x2v. And so then this will give me, oh, and this is defined for negative pi over 2 is less than x2 is less than pi over 2. So then this gives me z1 dot is z2, and this gives me z2 dot is v. And so now I'm going to make the v be something that will cause the v's closed loop dynamics to be asymptotically stable. So I want the eigenvalues of the resulting linear system over here to be negative. And so that's kind of great, I guess, in the sense that, like, wow, isn't that cool? I was able to design a feedback controller that brings Z1 and Z2 to their 0 values. And then you could say, what does that mean? So if Z1 goes to its 0, X1 is 0, and then if Z2 goes to 0, then it would be sine inverse of 0 is X2. So you can say, oh, isn't that so great? I'm able to stabilize that point. And then you can say, like, okay, but that doesn't help me next time, because how did I know to use this really cool transformation? And how do I know there is a transformation that exists even that is invertible and stuff like this? And then, so this is where we get a statement, and so we will talk about that in a minute.